we'll do this for as long as the Wi-Fi will let us, and then if not, I will, I guess, sit here and just narrate by myself, and then I'll go home and get warm. So we spent last week talking about the muscle side of things. Today, we're going to begin to talk about the nervous system side. So how does the brain communicate with your muscles, right? So that if I ask Lindsay to stand up and like dance around and do something that she actually, you don't have to, Lindsay, okay? That's for a different day. And when we talk about autonomic nervous system function, fight or flight kinds of things, then we'll make somebody stand up and sing or something, okay? We'll talk about how the brain communicates through the spinal cord with the muscles so that you can create voluntary movements, okay? So we're going to start off then and really spend all of our time at the spinal cord and below, okay? We're not going to talk, this is not a class in neuroscience, it's not a class in even like psychology where you talk about brain anatomy or different brain regions and what's going to contribute to what. We're really just going to focus on spinal cord and below, okay? So, in the spinal cord, you have a collection of nerve cells that are called motor neurons. Motor means movement in this particular instance, okay? We often will call them a motor neuron or an alpha motor neuron. Those terms are going to be used relatively interchangeably, right? If we look at the structure of a motor neuron, it's going to look like what you see on the screen. You're going to have the thing that most people think of as a neuron, which is what we call the cell body, okay? This is what we're going to think of typically as this is the cell, this is the piece that's going to sit in your spinal cord, okay? Nervous system, like your brain, is made up of a bunch of neurons. It's a bunch of these little nerve cells plus a bunch of kind of helper cells that are all around. In the spinal cord, you're going to have a collection of these cells plus also some things that we're going to see later that are called axons and some dendrites. So the cell body sits in the spinal cord. We'll talk about how the cell bodies of motor neurons that connect to a particular muscle are all going to be grouped together. And they're all going to be grouped in a very particular location, kind of, my anatomy words again are escaping me. I call them up and down, basically, like at different vertebral locations, okay? So cell body, inside the cell body is going to be the nucleus. This is the place where that neuron is going to make neurotransmitters and all the things that it needs to stay healthy, okay? Around the cell body are these little projections that are going to come off, as you guys can see up and around here, okay? Those projections are called dendrites. And so dendrites are structures that allow the cell body to gather information, to pick up signals from surrounding neurons, okay? Or the kind of immediately surrounding environment that's going to be there. Then going off the other direction off of the cell body is going to be a structure that is called an axon. Now, when I tend to think of nerves, especially when we think of nerves that are going to exist outside of the spinal cord, what you tend to see when you dissect a cadaver or like you bump your elbow or something, right? What you are thinking of as a nerve is really an axon, okay? It's really an axon. So the axon comes out of the spinal cord, projects out of the foraminal space, and then it's going to travel out down a particular location, and it's going to go from that location in the spinal cord out to the particular muscle that it innervates, that it's going to connect to, okay? Axons can be of different sizes. They're going to start off relatively big, and then they're going to branch off down. As they get into the muscle, they're going to branch off into these axon terminals, and then the ends of the terminals are going to have these little bulb-like structures on them called synaptic knobs, okay? Or sometimes it's called a bouton or a bulb-like structure, and those are going to be the places that are going to come in close contact with individual muscle fibers. Axons typically have a fatty sheath around them called myelin. Myelin increases the conduction velocity, makes impulses move faster. Okay? There are some degenerative neuromuscular disorders where you lose the myelin, okay, on those axons, and it slows movement down. It makes you feel more uncoordinated and things of that nature. Right? So that's how this is going to work. So we have cell body in the spinal cord. This is the alpha motor neuron. It uses these dendrites to gather information to decide, do I generate an action potential or not? And then it has this axon that's going to basically be the way that we communicate. That's the cord. You guys don't know what a telephone that would have a cord on it is anyway, so never mind. Okay, but this is the connection between here in the spinal cord to the brain signals down the spinal cord to these, and then the axon brings it out to the muscle. All right? So all of this happens very, very quickly. You think about moving and you move almost instantaneously, right? There's very, very little delay. So in some instances, if I tell you, right, wiggle your toes, you're wiggling your toes. Everybody wiggle your toes. You're sitting at home, wiggle your toes, okay? You are sending an impulse from the motor cortex in your brain, right? This is a relatively complex thought, down the spinal cord to the alpha motor neurons that are then going to connect to the muscles that move your toes. You have axons that are going to run from probably S1 or S2 in your spinal cord all the way down your leg, right? So that's several feet, and it goes really quickly, right? So imagine people very, very tall, basketball players, right? These guys or ladies, things they move really, really quickly. So we're going to talk about how fast this goes and why the way that we signal, the things that we use to signal, allow that to happen. Because if we did not use electricity, if we didn't have myelin, if we didn't use dendrites in the way that these things function, you would not be able to move very quickly. And tens and thousands of years ago, we all would have been, eaten by mountain lions or saber-toothed tigers or run over by woolly mammoths or whatever. Okay? So that part's really, really, really important. That's how structure is going to help us impart function. Okay. So I'm going to leave the slide about sulfatory conduction up here. We don't really talk about it very much. I'm sure you guys talked about it in physiology, but this is the idea that how having myelin increases conduction velocity, or the ability to move an electrical signal, which is an action potential, down the axons, okay, by having the myelin on here. And it's a process where there's myelin, and then there are these areas that are called nodes of Ranvier, where there is no myelin, and it's at those nodes where these have this very, very high concentration of these voltage-gated sodium channels. And so we're going to then get what in essence looks like a jumping of action potentials from one node of Ranvier to the next, to the next, to the next. And so that speeds up conduction. Okay? We're not going to get into sort of all the mathematics of this or any of those things. I just want you to appreciate that that's what's going on. Okay. The next piece of this to understand, now that we have a little bit of an idea about some basic anatomy, is the idea of something called a motor unit. Okay, a motor unit. So a motor unit is one alpha motor neuron and all of the individual muscle fibers that alpha motor neuron's axon connects to. Okay, one motor unit. In the nervous system, a motor unit is the functional unit that the brain can turn on or off at any given period of time. Okay? Remember, on the muscle level, it's the sarcomere where all the action between the actin and myosin are going to work and those kinds of things. In the nervous system, you can turn on things one motor unit at a time, or turn them off one motor unit at a time. So in a given muscle, there are going to be hundreds, if not thousands, of individual motor units. Okay? So for your bicep, let's just say, okay, guys got to be impressed with what a bicep is. Right? In your bicep, you have several hundred motor units. So that means you have, in your spinal cord, you have a corresponding number, so several hundred motor neurons, which are going to send out their axons and connect to the individual fibers in that bicep. Okay? So the bigger the muscle, in general, the more motor neurons that are going to connect to it, so therefore you're going to have more motor units. Right? Small muscles like the muscles in your eye, very few motor units. Big muscles like your quads or your glutes, thousands and thousands. Within a muscle, okay? So within a muscle, you're going to have some motor units that are going to be small and some that are going to be large. And then they're going to exist a whole bunch of them in between. When I say small versus large as it relates to motor units, what I mean is how many individual muscle fibers does the axon of that motor neuron connect to? So a small motor unit may connect to 10 or 20 individual muscle fibers, and a large motor unit may connect to several thousand individual muscle fibers. Okay? In every muscle in your body, you have some small motor units and some large motor units. Okay? The arrangement of these and the types of fibers that are going to be contained in each of these is going to become very important from a functional standpoint. Okay? So, small motor units. Okay? So the motor units that have the fewest number of muscle fibers in them tend to be almost exclusively made up of slow twitch muscle fibers. Okay? I should also probably clarify, in a motor unit, every muscle fiber is of the same type. Okay? Every fiber is the same type. So small units are, the smaller the unit, it's like in one motor unit 1, all slow twitch. Motor unit 2, all slow twitch. Motor unit 7 or 8, maybe it's going to be type 2A. Motor unit 8,000 in a big muscle, all type 2A. Okay? This is going to become really, really important. So the size of the motor units, because we can turn them on one at a time, is going to control for us the increments in force that we can generate. And I'll explain all of this and show this to you in the coming slides. Okay? Are we okay with that? A motor unit is motor neuron and every fiber that it innervates. Good deal. So if we look at all of this, there's this very orderly arrangement. So here is a, what would this be? It's not really a transverse cross-section of the spinal cord here, but what you can see is the cervical vertebrae are at the top. We're going to go cervical vertebrae, thoracic vertebrae, through here, lumbar, sacral down here at the bottom. And so what you guys can see is that the motor neurons for a particular muscle are going to be grouped together in a similar location in the spinal cord. So what you can see is up here in the cervical region, let's just say it like C3 and C4, that's where your diaphragm motor neurons are going to be. At C5 is deltoid and bicep, C6, wrist extensor, C7, tricep, C8, hands, right? Relatively upper body muscles here, okay? In the thoracic vertebrae, there's actually very, very few motor neurons, mostly internal and external intercostal muscles, okay? We're going to have down here in the lower thoracic vertebrae, sort of abdominal muscles and things. And then we're going to get down into the lumbar region, and it's going to go hip flexors, knee extensors, dorsiflexors, right? Toe extensors. Then we're going to get all the way down here in the sacral, where you're going to get plantar flexion. And then the very, very bottom is going to be, if you've got a little bit, although some of this is going to be involuntary, but like bowel and bladder, okay, those sphincter muscles and those kinds of things that are going to be down there, okay? So what this tells us is that basically all of my bicep motor neurons are going to be near each other at approximately vertebrae C5. Okay? So they're all going to be there. So there's some good to all of this in that because they're all located in roughly the same place, you can turn all of them on or off at roughly the same time. It's not like I have some bicep up here at C5 and I got some more bicep way down here at L5, right? Which would be weird because then, because of just the physics of everything, as we go from the motor cortex, it moves down the spinal cord in this way. These would get turned on, and then there would be a little bit of a time delay before I could turn on the ones that were down there. And what if that muscle was really important? Like I needed to jump out of the way of a car, or I don't know, what else you do with your bicep, right? Punch somebody behind you or something. And so that's going to be some of the utility of having all of them together. The bad part about them all being together is that if you damage the motor neurons or you damage the spinal cord, then you tend to lose the entire function of a muscle, right? If the lesion is at that area or the damage is at that area, or you often lose everything below all of them. Which is one of the reasons it's really interesting that the diaphragm occurs at closer to the brain at these in like C3, C4, even though the diaphragm anatomically, right, is going to be what you might think of as being distal to, right, the hands and the triceps and these kinds of things. So that's where they're going to be located. All right. So let's talk now a little bit about kind of what happens at the end of the axon, where we're going to make contact or very close contact with our muscle fibers. We'll learn a little bit about this, and then we'll try to put the whole thing together on how it gets turned on and turned off. Okay? The area where the terminal of the axon comes into close contact. Remember, it does not actually physically make contact, but where it makes close contact with the muscle fiber is termed the neuromuscular junction. Okay, it's called the neuromuscular junction. And this particular area is very, very highly specialized. Okay, and it is specialized so that we can have fast and efficient transmission of a signal from the nervous system to the muscle. Okay, so we can turn things on and turn things off very precisely and very, very quickly, and also do it with a minimal use of our neurotransmitters. All right. So what you will note is here's a muscle fiber, here's our axon coming down, and then it's going to branch off into these terminal ones, and you're going to have multiple of these kind of junction areas spread along a particular region of the individual muscle fiber. Okay? At the end of each of these little terminals, you have a thing that looks like this here, the picture here on your right. Okay? And so here's the nerve side on the top, and then here is the muscle side on the bottom. So you've got the end of the axon terminal, sometimes called the bouton because of the bulb structure here that's going to bulge out. Okay? And then this is going to be the cell membrane of a muscle fiber. So this is the sarcolemma down here on the bottom. So if the nerve side has this bulbous structure, the sarcolemmal side has these additional folds in it. The membrane folds up in this area right underneath. The bulging on the nerve side and the folding on the muscle side both serve the same purpose. Okay? That purpose is to increase surface area. Increase surface area. It's much like, you know, you have like 30 feet of small intestine like all like wound up inside your body, which always like still fascinates me to this day. Okay? And so what that does is it increases surface area on the nerve side so that we can release acetylcholine, and it increases surface area on the muscle side so we can have more and more receptors for acetylcholine here. And what that allows us to do is to very efficiently release a certain amount on the nerve side and then bind and trap that on the muscle side so that we get very fast, very efficient signal. Okay? What I do want you to know is that this signal, you have an electrical signal in the nervous system, so you have an action potential. And then at the neuromuscular junction, that electrical signal gets turned into a physical neurotransmitter signal, and it uses acetylcholine. I want you to know ACH. I want you to know acetylcholine. Okay?
Can you repeat that?
Absolutely. On the nerve side, from the brain to the alpha motor neuron, all the way down to the axon terminal, the signal is almost exclusively electrical. So it uses an action potential that it generates to move very, very quickly. When that action potential reaches the end of the axon here, when it gets to the axon terminal, that change in membrane potential is going to cause the axon terminal to release a physical signal, okay? These molecules of acetylcholine out into the neuromuscular junction. That acetylcholine binds to acetylcholine receptors on the muscle side, and then that's going to lead to the generation of an action potential on the muscles. So nervous system, electrical signal, physical signal to cross the neuromuscular junction, electrical signal again then on the surface of the muscle. Okay? Cool. All right. So I already mentioned an action potential. So an action potential is a brief electrical signal. It's like a single zap of electricity. We say that it is propagated. That's just a fancy way of saying that it's moving. Okay. Action potentials get generated and they move down along membranes. Right. And so as they move, they're going to basically flip the charge like a bolt of lightning, moving down through the nervous system, down an axon, okay, or if it's generated in the muscle, across the surface of those muscles. Okay? The action potential is the first step in a muscle contraction. You generate action potentials in the motor cortex in your brain, and that starts the entire process. Okay? In theory, then, if I can give you a drug that prevents the generation of this action potential, then a muscle contraction may not be possible. This is one of the ways that general and local anesthetics work. If I inject your leg with something called xylocaine, what it does is it basically deadens it. Like you can't feel things because you can't generate action potentials in those 3 and 4 afferent nerves to signal to your brain. And if I give you enough, it may also knock out the motor nerves as well. And so you can't communicate from your brain. If your brain says contract your muscle, and you're going, I'm trying, but it's not working, right? You ever been to the dentist? You get a filling, or you get your teeth pulled, and they shoot you up, and the whole side is numb, and your face like droops, and you're drooling all over yourself. That's because the anesthetic has one of the consequences. What they really want is that you don't feel things, but it also tends to knock out the function on the motor side as well. There are certain kinds of drugs that only work on the motor side, and some that only work on the sensory side. And so I'm happy to tell stories about all of that. These are also going to be areas where, like snake venom or spider venom, or some octopus have certain things, or like the pufferfish. If anybody eat sushi? Sushi people? Okay. I think it's illegal here, but you can go to Japan and you can get pufferfish. And if they prepare it wrong, it will kill you. Right? And so because it has a neurotoxin in it, and the neurotoxin prevents the release of acetylcholine, and so you can't contract your diaphragm and suffocate basically. So I don't want to go pay like $1,000 for like 2 bites of raw fish that might actually kill me. That seems pretty crazy, but that's some people's thing. All right, so that's kind of how all of this works. Okay, that's how all of this is going to work. So brain action potential. Action potential moves down the spinal cord. Action potential hits the motor neuron. It runs through the motor neuron, down the axon, gets to the axon terminal. We release acetylcholine. The acetylcholine binds to the acetylcholine receptor on the muscle, and voila, that generates another action potential here along the sarcolemma. Okay? We're not going to get into sodium and potassium channels and how we do all of this and how we repolarize, whatever. But it's going to move along the surface, and it's going to go along. It's going to come to those T-tubules, and the action potential is going to run down the T-tubule, down into the inside, okay, of those muscle fibers, And then that T-tubule, by it depolarizing, is going to tell the sarcoplasmic reticulum to release calcium, and then calcium is going to bind to a regulatory protein on actin, and that's going to allow actin and myosin to form what we call a crossbridge. Okay, so we'll get into the kind of functioning of these individual things in just a second. I assume you guys have at least heard of this before, right? You guys get this in physiology and all of these things. Okay. So what I want you to take away is there's a lot of steps here, a lot of places for something to go wrong. Okay. It always amazes me that we can ever do anything in our body, right? Like I want to, move and wiggle my fingers, but somehow that still happens and nothing ever goes on. You like do your dissections and you saw like how small those axons and those nerves and things are. Think about all the times you've fallen down in your life, right? I don't get how we don't just rip those things to shreds. Like, oh, I fell on the ice on our front steps this morning, okay? And I should have like ripped my femoral nerve in half or something just by doing all that because I'm an idiot. Okay. All right. So let's see how I'm doing on time. So it's new. All right, we're doing okay. So the process that I just described to you guys is something called excitation contraction coupling. The process of the T-tubules telling the sarcoplasmic reticulum to release calcium, that calcium binding to a regulatory protein on the actin filaments called troponin, and then the formation of the contact between actin and myosin, which is called crossbridge. This process is called excitation contraction coupling. Okay? The mechanism by which intracellular calcium is released and we get a muscle contraction. Okay? So we need action potential in the T-tubules. Those T-tubules are going to signal to the sarcoplasmic reticulum at a particular channel called the dihydropyridine channel, which then opens the ryanodine receptor, which you guys don't have to know, and we get this release of something of the calcium. Okay? All right. On the actin filament, there are two regulatory proteins. Okay? Two regulatory proteins. One is called troponin. The second is called tropomyosin. All right? Anybody ever had a cramp? Anybody ever had a cramp? Several of you have had cramps, okay? A cramp is basically a muscle contraction that you don't want to have, right? Like you're not actively trying to contract your muscle, okay? So when you get a cramp, there is, not from the motor cortex, but there is some sort of a signal from someplace downstream of that that says, make that muscle contract. And you can't turn it off and you can't relax it. If we did not have troponin, okay, and we didn't have tropomyosin on our actin filaments, your normal state of existence would be a whole body cramp, okay, without tropomyosin. So tropomyosin is a protein, and it sits and it covers up the binding site for myosin on the actin filament. I will again use a child-proofing thing because my daughter wants to get into everything this weekend, and she learned how to climb up on our bar stools all by herself. She thinks they're fun because they're like tractor seats, they're metal, and you can spin around on them, and she thinks that's like the biggest fun. But of course it has no back, and anyway, she could fall down. So think of tropomyosin as those little plastic coverings that you put into electrical sockets or electrical outlets so that kids can't jam their fingers or pencils or Lord only knows what else in them, okay? That's what tropomyosin does. Myosin wants to bind to actin very badly, okay? Very, very badly. It's very needy in that way, okay? It wants to grab onto actin. So we need the tropomyosin there so that it can't do that. Well, that's fine right up until you need a muscle contraction, until you need to move and do something. So we're going to use troponin, which is going to be connected to the tropomyosin. We're going to put a signal, this calcium is the signal, onto troponin. It's going to change its shape, and that's going to pull the tropomyosin out of the binding site and then allow myosin to connect to actin. And then when we turn off our muscle contraction, The myosin lets go. The troponin goes back to normal. The tropomyosin goes back into the binding site. Okay? Does that sort of make sense, guys? Sort of makes sense. The binding of myosin to actin is going to form something called a crossbridge. Right? Think of it this way. My arm is the actin molecule. Okay? My other arm that is bent, this is the myosin. Right? Normally it's trying to bind, it can't. The tropomyosin is in the way. It's open, it's grabbed on. All right? Once the myosin grabs on, it's going to change its shape and it's going to pull. So it binds. We've now formed what's called crossbridge. We can now generate force, and it pulls on the actin, and that's going to pull my muscle and make my muscle short. Then it lets go, okay? And the tropomyosin can go back, so now it can't bind again. We get more calcium release. It can bind a second time, and it can pull even farther. Okay? So when they attach, we call that a crossbridge. And then assuming that the external force is less than the force the myosin can generate, we get something called a power stroke. Right? The power stroke is the tilting of the myosin that pulls the actin. That pulls the actin. So the excitation contraction coupling that lets us form a crossbridge. Then we get a power stroke. So this is where we're going to get our force production that's going to allow us to. Okay. This stuff is unbelievably important. If you can't do this, you can't breathe. Okay? Can't do it, you can't breathe. You can't do this, you can't walk, you can't run, you can't talk, you can't blink your eyes, you can't do anything. So here's just kind of a cartoon of all of this. Now, somebody said they tried this video, the sliding filament theory of contraction, and the video didn't work. So the link doesn't work. Did you try to copy and paste this into a web browser to see if the YouTube video still exists?
No.
Okay. Video unavailable. How dare they try to like copyright protect stuff? Okay. I will find us another video. They pulled it down for me. Okay. But the idea of the sliding filament theory is just that here's your actin filament, myosin binds, the myosin heads tilt, and they pull the actin, like in this instance, they're going to tilt, right? And they're going to pull it from right to left here. They're going to slide this filament in this direction. So every time you generate movement, every time I'm doing a bicep curl and I'm picking up a weight like this, I'm getting thousands and thousands and thousands of cross bridges, and then thousands and thousands of little shortening movements from those myosin that allow me to pick up my arm. Okay? So we talked about most of those things. Now the really fun part, okay? This is something called the Crossbridge cycle. What I'm about to tell you is maybe to me the most backwards thing in the entire existence of physiology, okay? In the entire existence of everything. It's going to seem very counterintuitive, okay? Very, very strange. Can I get a volunteer? Can I have a volunteer? Anybody want to volunteer? Okay. Bria? Okay. Bria, would you stand up for us, please? Okay. Bria, did you work out this morning? Do anything fun where you might be tired or anything? No. Okay. All right. So, okay. Hold that thought, Britt. Zoomers, are y'all still here? It's still recording. Okay, Johnny says yeah. Okay, well, guys, we don't know what happened. It like locked out of the share screen. But I think we're back. Okay. All right. So, Bria, could you, to demonstrate what this is going to be, Bria, could you do like half squat, like just squat down and hold it for us, please? Okay. So we're imagining now, okay, she's doing a half squat. We want her quads to do a crossbridge cycle, so just stand up. Okay? Thank you. So just Hang tight for me. So in a cross-bridge cycle, actin and myosin are going to go through these 4 very distinct steps, okay, where we're going to attach them. We're going to get a power stroke, which is, so when we had Bria squat down and we say, attach the myosin to the actin, as she comes up, right, her quads and her glutes are doing the power stroke that are going to allow that raising up to happen. Then we have to do it all over again. So we have to break the myosin off, and then we've got to sort of cock the myosin head and it can start over again. So how difficult was that for you to do? Wasn't too bad. If we gave you more weight, it might be worse or something, right? Okay. What I'm going to ask you to do now is going to be very simple. I hope that it will illustrate what's happening. Okay. For the folks on Zoom, we're not going to turn the camera around. We're going to have Rita walk up a step for us. Then we're going to have you walk down the step. All right, so walk up the step for me. Perfect. She's doing, in her quads, thousands and thousands of individual cross-bridge cycles to walk up, okay? Now turn around and walk down. Perfect. Thank you. You may sit down. Bria, of those 2 things, what was more difficult?
Like, squat?
No, I'm sorry. The up the stairs or the down the stairs? Okay. If I made you do that over and over and over again, would you rather go up the stairs or down the stairs? Probably down. Okay? And the reason that going down doesn't feel as difficult is because it does something different in the cross-bridge cycle, and it very distinctly illustrates why this doesn't make much sense to you. Okay? So, in your normal resting state, you're relaxed. Your myosin molecules have ATP bound to them. Okay? And it's going to be bound as a molecule of ADP and a molecule of inorganic phosphate. Which one of you is doing this? I don't know what's happening. This is so good. Okay. I've totally lost all train of thought. We're here, we're bound, right? It does the power stroke and it shortens. So Bria's walking up the stairs, it is short. Okay? When it has done that, it has kicked out the ADP and it's kicked out the inorganic phosphate. You've moved, but you've not yet used any energy whatsoever to do this. None. Zip, zero, zilch. Where we use energy in a muscle contraction is not to cause the power stroke to happen, which is what everybody thinks, because it makes sense. I have to move, right? It's like pressing on the gas pedal on your car. In fact, where we use energy in a muscle contraction is not to get attachment or to get a power stroke and generate force. We use energy to come in and tell the myosin to please stop being creepy and let go of the actin. Okay? You use energy to break cross bridges apart from each other. So the ATP comes in, the myosin lets go of the actin, right? Then we're going to hydrolyze that ATP into ADP and inorganic phosphate, and that will return the myosin head to its high energy state, which I like to think of as it's like pulling the hammer back on a pistol. It's recocking the myosin, and then it waits until the tropomyosin gets moved again, and we can start the whole thing over. So as Bria was doing her squat, as she was walking up those steps, this entire process is happening thousands and thousands of times in her quads. Okay? When she turns around and she goes down the stairs, because that's an eccentric. This is the universe telling us we're supposed to stop, right? It's just that you do an eccentric contraction, you don't have to break the cross bridge. So it doesn't cost you as much energy, which is why it's easier to run downhill or to walk down the stairs than it is to go upstairs. It's the actual physiology. So you guys will see, okay, on Wednesday, we'll have somebody, like I'll give them a weight and we'll make them do like curls where they'll pick the weight up the whole time and never let it down, and we'll see how many reps they can do. And then we'll flip it around and we'll see how many they can do just lowering that. Okay? And those two things are going to be different because of how the Crossbridge cycle functions. So this is really, really important, guys. I want you to know this particular picture by heart. I want you to know where actin and myosin are bound to each other. I want you to know what's happening with the ATP and the ADP and things all along all. We'll reinforce more of this as we keep going on. Okay? Questions so far? Okay. Great question. Okay. Maybe in the next slide. So there are 3 types of muscle contraction. Okay. No, there are 3 types of muscle contractions. So it's a contraction where the muscle shortens. Okay. So the myosins are doing lots of power strokes. They're all pulling on those actin molecules in the muscle. So this is I curl up with my bicep. This is what's called a concentric contraction. The bicep is short. And you then take the weight from up here and you lower it back down. The bicep is lengthening. That's called an eccentric contraction. And when I take this and I just hold it statically so that the muscle is not changing the weight, that's called an isometric contraction. And so I have several slides. They must be a little bit farther on about concentric versus eccentric versus isometric contraction. Okay? Yes. That's right. So as Bria's going up, right, she's doing concentric with her quads, eccentric with her hamstrings. As she goes down, it's concentric with her hamstrings, eccentric with her quads. That's right. So we call those like agonist and antagonist muscles, those muscles that oppose each other. They tend to kind of, when one is doing concentric, the one on the other side of the joint is typically doing eccentric. Okay? It's a very good question. You guys get that a little bit in anatomy? You always talk about like agonist and antagonist muscles and those things. Okay. If anybody's had biomechanics or anything with Dr. J, then y'all will talk more about kind of all of that as we get into the biomechanics. Okay. So we'll talk about motor unit recruitment and kind of how all of this is turned on and it interacts with the muscles until this quits on us again, and then we're going to call it again. Okay. So will you do me a favor, Lily? Can you stand up? Can you stand on one foot? Okay. Can you hop on your one foot just barely a little bit? Okay. Now can you sit down? Do you have a pencil? Okay. Can you spin the pencil around like on your fingers, just like kind of twist it like this a little bit? You can't. That's okay. Even better. Okay. So, Lily, if I ask you, which of those things took the most force, like required you to use the largest amount of muscular force to perform? Hopping on one foot, okay? I asked you to hop just a little bit. What if I'd ask you to hop as high as you possibly could? Could you have gone a little higher? Maybe if we weren't worried about like falling down or something, right? Maybe a little bit higher. So did you have more force you could have generated potentially as you're sitting here hopping? Okay. So the point I want to illustrate is that movements are complex. Okay. By having Lily hop, she was contracting many muscles all at the same time. And all of them had to be contracted at just exactly the correct amount of force so that she hops a little bit, but not so much that she loses her balance, right? As you're going up, you're holding your chest. in a certain way, you're holding your shoulders in a certain way. So you think I'm just using my leg as I'm hopping here, but I'm actually contracting many, many muscles to hold my posture and all of this. If I get any of those things wrong, I fall over, right? Or I jump too high, or whatever it's going to be. You're writing and you do too much and you slam your pen. Can you imagine that? Like, you've ever watched a toddler try to color? My daughter does not know how to gently color. She just grabs it and just grinds it in there, okay? So that's a level of fine motor control that comes with practice. And so the reason that you can so very precisely control the amount of force you generate, and therefore so finely and precisely control movement, is because of the manner in which we turn on or recruit motor units of each individual muscle, and this idea of what we call activation. So you can turn a motor unit on or off, and then once it is on, we can modulate the number of action potentials going through it, and both of these things allow us to precisely control just very, very finite amounts of force, or finite increments of force that we generate from a given muscle. Okay? So, the idea of recruitment, okay? Recruitment is on or off of a motor unit, right? So the brain sends a signal and it turns on a particular motor neuron in your spinal cord, okay? When that motor neuron gets turned on, it is going to make all of the individual muscle fibers to which it connects contract simultaneously. Okay? You recruit muscle fibers, or you recruit muscle one motor unit at a time. When we had Lily Hop, she was probably recruiting several hundred motor units in her quad. Okay? You think of it as we turn them all on at the exact same time. That's actually not what happens. There's tiny, tiny bits of lag in there as you go, I need this much force, so I'm going to match what I want. Anybody ever picked up a box you thought was going to be really heavy and it was empty? Right? You lose your balance, you throw it backwards really like that. Okay? Every time you go to do a movement, your brain, based upon previous experience, estimates how many motor units in a given muscle it's going to need to turn on to create the movement that you want. Okay? And so sometimes it gets it wrong. But in general, it's very, very good. You do something once and it remembers. Okay? This is like when they say you learn how to ride a bike, you never forget. You learn that movement pattern. You learn that pattern of, okay, these postural muscles, then it's this muscle in my quad, then it's this muscle in my plantar flexors. It remembers how to do all of this. Okay? So if you need more than one motor unit, there's a very distinct pattern in an orderly manner in which we decide which motor units to turn on and which ones not to turn on. Okay? We call this the size principle of motor unit recruitment. Right? The size principle. So we are going to turn on the smallest motor units in any muscle that's being used first, and progress from small to a little bit bigger, to a little bit bigger, to medium, to a little bit bigger, all the way up to our large motor units. Right? And so by adding each additional motor unit, you add a small amount of force, and that lets you precisely control what you need. Okay? If you guys remember, the fiber types of those small motor units are slow, which means they're very resistant to fatigue. And so when you're doing movements that you do very, very often that require very low levels of force, things like standing, things like breathing, things like walking, you're always using the same motor units over and over again, which is good then if they're very fatigue resistant. Okay? So this is just going to show us the percentage of your total active muscle fibers in the muscle. It shows the relative exercise intensity. So this is basically 100% of your VO2 max. So this is like this kind of high intensity of aerobic exercises you can perform. Here's not moving at all, right? 20 or 30%. This is walking kind of right in there. And so you're going to turn on a few motor units. They're mostly going to be type 1 or slow twitch. I need to go a little bit faster, so I'm going to turn on a few more and a few more. And I now have all of my ones. All of these are going. Then I'm going to add in some of my 2A's. I know you get bigger and bigger. So I'm going from walking to jogging. While I'm jogging, all of this muscle is still being used. Then I'm going to add on these. And I'm going to go faster and faster. I'm going to turn on more and more and more until finally I get up into these 2X spots. Okay. And so it looks a little bit of something like this, right? Number of active motor units, the amount of force. I need very little force, so I turn on type 1 motor unit. It's these small ones that only has a few number of fibers. That's not enough force. I need more force. Turn on the second. I need more force still. Turn on a third one, okay? And then in theory, I keep doing this until I've used up all of my slow twitch ones, and then I get into and I turn on a 2A, and then another 2A. I need more and more force, and eventually I'll turn on a 2A. So here's my whole muscle. These are all these individual. Okay. Does that sort of make sense to you? Just kind of following along with me? Okay. Cool. Talked about this. We talked about those kinds of things. All right, we're going to stop. We'll pick up with contraction velocity and force development on Wednesday. Where hopefully, even though it will still be cold, it will be a day where less things have gone wrong.